everyone. My name is Jason Chang from KGSEA Math Circle, and today I'm going to give an introduction lecture on deep learning. This presentation is going to proceed in the following order. First, I will provide a definition of deep learning with an example that we will stick with throughout the lecture. Then, we will discuss the key components that allow deep learning to occur, weights and biases. Finally, we'll dive deeper into how these weights and biases can be altered to improve the performance of the prediction model. The lecture will close with possible extension topics to better our understanding of various AI models. First of all, when we talk about deep learning in the context of neural networks and machine learning, we mean an artificial neural networks with input, processing, and output layers, which can improve over time with iterations of test cases and learning. We'll use an example of image recognition, specifically where we input the AI an image of anything of our choice, and it spits back out a description of the image. Although not the most accurate analogy, we can build a strong understanding through the following metaphor. We'll consider the input layer to be what the computer receives, such as the values on each pixel in numerical form. Then we can imagine the hidden layers to be the smaller points of the image that the AI can notice, such as lines and curves, shapes and features, and individual objects like leaves or tree. Then our job is to understand how these individual nodes can be activated and how each layer can communicate with each other through weights and biases. To understand weights and biases properly, let's discuss a simple example of one processing layer to another. First, each node that we saw on the diagrams above can have a value called activation status. This is an indication of how sure the program is that the value exists. In the example on the slides, we can see 3 statuses, each indicating head, fur, and wings. What happens for each of the output layers is that for each value of the previous layer, the activation statuses are multiplied to each weight, which decides how important the relationship between the nodes are. For example, if the model notices head in the image, it will indicate it with a positive weight towards bear. Similarly, fur will positively indicate that what we're seeing is closer to a bear than other objects, and with more certainty than head. This suggests that W2 can be a greater positive value than W1. Conversely, the presence of wings will make it less likely that the image in discussion is of a bear. Therefore, W3 can be a negative value with a more significant absolute value. Next step in the program is to convert this sum of activations multiplied to weights and turn it into the next activation value. Here, a bias is a certain value that the sum has to exceed for the next node to activate meaningfully, such as saying that the sum must be greater than 10 for it to start counting it as an active node. Then an activation function of a choice will turn this value that exceeds 10 into a number between 0 and 1, passing on the activation status. With appropriate weights and biases, we can build a program that can reliably recognize meaningful connections that handwritten algorithms will never recognize. The beauty of deep learning and where the learning occurs is at the process of fine-tuning these weights and biases. To improve the performance of our neural network, we need to first figure out how wrong our program is. We can simulate this by adding up the squares of the differences between the output value that is desired versus what the program currently gives out. Since the cost is entirely dependent on what the values of each weights and biases are, we can model it as a function of multiple inputs, the weights and biases, and one output, the cost of this program. Here is what a model of the relationship between two inputs, weights or biases, and one output can be. Therefore, to minimize the cost, we need to travel across this space as given in the direction of the arrow, following the negative gradient of the surface. Considering the values of x and y to be weights, we can say that the most efficient way to reduce the cost, our z-axis, is to decrease x by about 0.5 and increase y by a value of about 0.75. This is how the machine learns. It takes feedback from the cost function to correct its weights and biases for more accurate outputs. Since there are multiple layers in the neural network, it's important to analyze what happens to each of the layers at each state. Because we can only impact the weights and biases of the program, we need to be able to decide which one should decrease or increase. In our example output of a bear, dragon, forest, and ocean, we can begin by deciding how much of each we need to alter. For example, bear has to increase a little bit, whereas ocean must decrease significantly to match our desired output. This can be done in two ways. First, to alter the weights of the layer right below, enhancing the relationship between head to bear or leaves to forest, and reducing the prediction of ocean from water. The second method, which propagates backwards throughout the program, hence the name backpropagation, is to change the activation of the previous layer, namely reducing the significance of water in the last hidden layer. This can be done by reducing the weights that affect water on the previous layer, layer 2, to decrease the activation value of water. Through this backpropagation, the machine will learn to produce more and more accurate output. We've looked at the primary structures of neural networks and deep learning. We now know that deep learning occurs through the help of weights and biases, and we know how the machine learns through minimizing costs, and that the process runs backwards through the hidden layers. Now, the possible topics that we can extend beyond to improve our understanding can be how this applies to large language models such as ChatGPT, and how language encoding differs from simpler deep learning neural networks, such as the example that we discussed, in terms of language encoding, transformers, attention, and multi-layer perceptrons. We can also look into different forms of generative AI, language, audio, and video, where they can take in these inputs or even spit out those as outputs. And finally, we can also discuss the effects of RLHF, reinforcement learning with human feedback, and how it plays in with weights and biases. Thank you for listening.